Well, my dear participants, today I am going to continue on the fitting of distributions using maximum likelihood estimation via optim function of base R. So, I have made certain modifications in my source code file. So, I would like to generate the PDF document also. So, here I will go into knit, and then knit to PDF. So, this will generate the PDF. Library doc. Oh. Well, I have to go into the source code then. Yes. So, I have to install this. Oh, I'm not sure whether it is connected to internet or not. Yes. Now it is connected to internet, and now I will install the package by using install.packages. So it is installing. Yes, it has installed the package dog. Yes. Now if we will generate the document, it will run now. It is generating the PDF document. Yes, PDF has already come. So we will go into the PDF W7, W7, and we will open this. So here we have already talked about. Yes. So we have already discussed these things. Here L theta is the likelihood function. The maximum likelihood estimate is obtained by mean of minus L theta by minimizing, and Hessian matrix is minus L double dash theta, theta is equal to that is equal to Fisher's information matrix, which is termed as Fisher's observed information matrix. It may be noted that the asymptotic variance of theta hat is I inverse theta hat. This implies that standard error of theta hat could be obtained by square root of diag of this matrix, inverse of Fisher's information matrix. Thus, 101 minus alpha percent confidence interval for theta could be theta hat plus minus q norm alpha by 2 lower dot tail is equal to falls into SC of theta hat, where SC of theta hat is equal to square root of diag solve I inverse theta. Introduction to the optim. I have already discussed these things. Now, we have already discussed these things. Now, fitting of Weibull we have already discussed. Assignment. Describe this fitted model graphically. So, we can describe this by just putting the estimates. Now, fitting a nonlinear regression model with optim. Fitting a nonlinear regression model with optim. We can fit a nonlinear regression model using optim. For example, we can fit a growth model defined as weight is equal to beta naught into beta 1 raised power age plus error for growth data of chicks weights and age defined as. See, actually this data on age and weight, it has been discussed by the great authors of statistical analysis. They are Snedeker and Cochran. And they have given this data set in their great book on statistical methods by Snedeker and Cochran. So, I have taken this data from there and they have fitted linear model, but here we are using the optim function to fit the same data, So, we will, because this text file contains, so we can read the data. Chicks is equal to read.table and chicks.txt, names, age, these are the column names, age and weight, and header file n is equal to 11. So, up to 11 observations we can see. Define a model in R, NLL rig, nonlinear regression, is equal to function of theta and then y and then comma x. So, here it is LL is equal to D norm because error distribution is normal. Normal with mean this one theta hat into theta 1 into theta 2 raised power x. So, this is the nonlinear regression model, and SD is equal to theta 3, log is equal to 2. And then we are returning some LL and we are returning negative of the NLL rig. So, it is minus LLL rig. Now, we can make use of fitting using optim. What we have done, we have selected y is equal to chicks weight, x is equal to chicks age, and then M1 optim par. We have 3 parameters to estimate. One is beta 1, beta naught, second one is beta 1, and third one is sigma. So, I am giving guess value to these values, to start the iteration, and the objective function to be minimized is NLL rig, which has been defined here, NLL rig. And C, Hessian is equal to true, y is equal to y, and x is equal to x. Actually, this model has been discussed by Snedeker and Cochran actually, and see, weight follows normal distribution with expectation of y or weight given x is equal to beta naught into beta 1 raised power age, and so this is the mean, and SD is equal to sigma. So the parameters which need to be estimated is beta naught, beta 1 and SD. So these are the three parameters which we want to estimate, and mean is the non-linear function of betas. So that's why it is non-linear model. So here we have given the guess value of beta naught, beta 1 and sigma. Fn is equal to LL rig and LL rig. Hessian is equal to true, y is equal to y and x is equal to x. So here par will talk about this is a vector of betas. And here y is equal to y and x is equal to x. So we have estimated these parameters, and ML estimator of beta naught is 0.00000020, and the estimated value of beta 1 is 1.572, and estimated value of sigma is 0.031, and the value of the log likelihood at optimum point is this, and this convergence 0 shows it is significant. Then Hessian matrix, actually this Hessian matrix is nothing but, actually it is minus L double dash theta hat, and that is nothing but minus L double dash theta hat. Instead of theta hat we have beta naught hat, beta 1 hat and sigma hat. So these are nothing but they are partial derivatives with respect to the second order L divided by del beta naught square, then in the diagonal del 2L delta beta 1 square, and here del 2L del sigma square, del sigma square. It is not writing del sigma square. Yes, it is sigma square. And here these are the non-diagonal elements. So we are extracting these diagonal elements and we are taking a square root of those. So this is the Hessian matrix. So this is the Hessian matrix we have got, and then we are extracting parameter values ML, M1 par, and SC is equal to square root of diag solve Hessian and then out R bind SE. So here I would like to change the names of the object out, because it is MLE, but here it is not showing what are the names. It is beta naught, it is beta 1 and it is sigma. So we should keep the names also, which we can do here. First I am reading the data. Here chicks is equal to C. This chicks.txt is already with this file chicks.txt. This file is already there. So this is the chicks data. which is saved in the folder, in the same folder. So what we have to do, we have to read this. Chicks is equal to read.table and chicks.txt the file name. So it will generate the data frame chicks, and then we can read names chicks, and then we can put the head 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 chicks. So this is the header part. If we will write tail, 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 so it will show from the bottom. So it will show the tails. Now I am going to define the function. Here NLLRig is the name of the function which is to be optimized. Function and argument are theta, y and x. This is the response vector, this is the regressor. This is weight and this is age. So LL is equal to d norm y, and this is the mean of the, this is the expected value of the function which need to be fitted. And this theta 3, SD is equal to theta 3, and this is the mean, and log is equal to true. So then sum LL, so it will generate the log likelihood values at these points, and then we will take the sum of the log likelihood values, and then we are returning negative of log likelihood. So to fit this, what we have to do, we have to extract y. Y is nothing but weight, x is equal to chick's age. Now we can fit optim. We have to run this. Now optim, here par, these are the guess values for the beta naught, beta 1 and theta and sigma. Fn is equal to, this is the objective function NLL rig. Hessian is equal to true, and y is equal to y, and x is equal to x, because y, this is the name of the y and this is the value of the y. Similarly, the name of x is the value is this one, that is x. And when we will run this, NL rig is not found because we have not run that. So first we will run, and then we will run this. See, now when we have run, we can run it again. See, so these are the outputs. Suppose we want names of out is equal to C. In double quotes, we can write this is beta 0, and then in double quotes we can write beta 1, and then in double quotes we can write sigma. So we are naming the column names of this out matrix. And now if you print out, here, we have to write call names. call names. So first I have to write here call names out. Call names is equal to and then out. So here it has changed the call names. Beta naught, beta 1 and sigma. So it has changed the names. So here we can add out, and after that out we can have call names out is equal to C. Inside this we have to write beta 0, then beta 1 and then sigma. So we have changed the names, call names, and then we can out the result up to, we can round the result up to 4 places of decimal. So out, and it is the 4 places of decimal. So round out. Now we can run these results and we can get yes. Now here the result has been modified. So these are the certain modifications which I made during the class. Now these are the these are the parameter vectors, this is the maximum likelihood estimator, and these are the Hessian matrix. Compare these results with NLS discussed in the next section. So in the next section we will discuss these results to obtain these results using using NLS function. Actually this is we are getting on the basis of optim, where you have to define the objective function, you have to guess the start values, all that. But NLS is a very simple function through which we will make all these fitting. Now I am going to talk about fitting with fitdistr. Fitdistr is a very powerful function. Fitdistr is available with the mass package Replay 2024. A large number of distributions can be fitted using this function. Fitdistr is a part of the package mass. Mass I have already praised. Mass stands for Modern Applied Statistics with S plus, and its 4th version, which was published in 2000 or 2002, it contains R commands also. Earlier it was being developed for S plus, and its package implementation, it is among the core packages. That means those packages are core packages which, when you recommended packages, when you download base R, there are certain around 25 packages which are downloaded automatically, and mass is one among them. So the function fitdistr, this includes normal Poisson t distribution. It can be reported as fitdistr x, then dense function name and start, where x stands for the data to be fitted, dense function stands for the name of the density function to be fitted, start stands for guess values to start the iteration. Let us begin with the gamma distribution. Library mass set.seed 123 x is equal to r gamma 100 observations are being simulated with shape is equal to 5 and rate is equal to 0.1. So fitdistr x is the data object and the function name is gamma. So we are getting here our shape is 5, here shape is estimated shape is 6 point something. Rate is 0.1, but here it is 0.13. And this is the standard error of shape and these things. Fitdistr x gamma. See, now do this directly with more control. Fitdistr x d gamma and then list shape is equal to 1, rate is equal to 0.1, lower is equal to 0.001. So these are the, because you know that for gamma distribution fx is equal to alpha raised power p, x raised power p minus 1 and then alpha raised power p, then x raised power p minus 1, e raised power minus alpha x, e raised power minus alpha x divided by gamma p. So this is known as gamma distribution with shape p and rate alpha. So here we put a restriction that alpha is positive and shape is positive and this one is also positive. Alpha is positive. So p is positive, alpha is positive. So that's why we are writing lower is equal to 0.001. And we are fitting this and we are getting the result. Assignment: fit gamma distribution using optim as discussed for Weibull distribution and compare your results with obtained using fitdistr. Simulate 30 observations from Poisson distribution with mean 10 and fit using fitdistr. So actually I will continue with the same video in my next talk.